Okay, 4.2 mean value theorem. This is the mean value theorem for derivatives. So if we have a continuous function on a closed interval, okay, and it must be differentiable. Okay, so not only does it have to be continuous, but it cannot have a corner, cusp, or vertical tangent on the indicated domain. There must be at least one point at which, okay, so basically our derivative, which is the instantaneous rate of change, is equal to the average rate of change. So here we can see slope of the tangent must be equal to the slope of the secant line. So again, if you have a continuous function on a closed interval and it must be differentiable, there must be a derivative equal to the average rate of change. So again, this is slope of the tangent, and this is slope of secant. So interpreting the mean value theorem, if a car accelerating from 0 takes 8 seconds to go 352 feet, its average velocity for the 8-second interval is 352 over 8 seconds. Again, if you're starting from, so think of your initial position, and then after 8 seconds, you're at 352. So if you're doing the average velocity, which we've done before, that's going to be 352 minus 0 over 8 over 0, which is how they get 352 over 8, which is 44, and it's going to be feet per second. Okay, that means from beginning to start, your car has to be going 44 feet per second at some instant, okay, at some time in between there. So let's take a look at example 1. State whether or not the function satisfies the hypothesis of the mean value theorem on the given interval. If it does, find each value of c in the interval AB that satisfies the equation. So we have, again, the hypothesis is that we have a continuous function on a closed interval and it must be differentiable. So if we look at f of x equals x squared, so that's a continuous function and we have a closed interval. So this one's yes, mean value theorem applies. And now what we want to do is we want to find f prime of c. Well, let's find f prime of x. F prime of x is 2x. Now they're just using this value of c, but we can just say f prime of c is 2c. Now we want to set this equal to f of b minus f of a over b minus a. So we have 2c must equal, again, here's b, here's a, so we're plugging into x squared. So we have 2 squared minus 0 squared over 2 minus 0. So we have 4 over 2, which is 2. So c equals 1. So here, and there's a picture here, you can see right there, when we have the point 1 comma 1, that has the same slope as the slope from 0, 0 to 2, 4. Okay, next one. Again, we want to check to see, does the mean value theorem apply? So first thing I notice is that square root of x squared is really absolute value of x. Now this gives us a corner at x equals 0, which is a problem because x equals 0 is in the domain that we were provided, which is from -1 to 1. So no, mean value theorem does not apply. Okay. Next one, f of x equals natural log of x plus 1 from 0 to e. So this is going to be differentiable on its domain, which would be when x plus 1 is greater than 0, so when x is greater than -1. So since we're looking at this interval, that does apply. So, and this is a continuous, it doesn't have any corners, cusps, or vertical tangents, so mean value theorem does apply. So we want to do f prime of x first. So that's going to be 1 over x plus 1 times 1. And we know we want, so that's going to be 1 over c plus 1, that's f prime of c. And we want ln of e plus 1 minus ln of 0 plus 1 all over e minus 0. Now, what ends up happening here, we get ln of e plus 1. This becomes ln of 1, which is 0. So we have that. I'm going to just take the reciprocal. So we have e over ln of e plus 1. So that means c is equal to e over ln of e plus 1 minus 1. And we could plug that into a calculator. And we have e divided by ln, and again, we can't distribute that, that's a function, ln. So e plus 1, and then minus 1, so I get about 1.0698. And just keep in mind, our answer needs to be in the interval that was provided at the beginning. So 0 to e, yes, 1.0698 does fall into that interval. Okay, so the next example, we are given an interval, and we also have a function that's provided. So we want to find the secant line, and then for part B, tangent line. So for part A, the secant slope is going to be equal to f of b minus f of a over b minus a. So that's going to be square root of 4 minus square root of 1 over 4 minus 1, so that's going to be 2 minus 1, so 1/3. Now, if I want to write the equation of the actual line, I just need a point and the slope. So I have a choice here. I can either choose plugging in 1 or I can plug in 4. Let's use 1. So square root of 1, I get 1. So I have y minus 1 equals 1/3 times x minus 1. Now for part B, I need to find the tangent slope. Well, the tangent slope is going to be f prime of x. So that's going to be, since square root of x is x to the 1/2, I have 1/2 x to the negative 1/2, or 1 over 2 root x. Now, I can find the slope if I knew the x value. I don't know what the x value is, so I go back here to secant slope of 1/3. So I want to make 1/3 equal to 1 over 2 root x. So I'll take the reciprocal both sides. So I get 3/2 equals root x. So 9/4 is my value of x. Now to find the value of y, sorry, not a lot of room here, but f of 9/4 is going to be 3/2. So my tangent is going to be y minus 3/2 equals 1/3, and then x minus 9/4. Okay, for number 2, let's find the secant slope. So my secant slope is going to be f of b minus f of a, so f of 1 minus f of negative 1 over 1 minus negative 1, which becomes 1 plus 1. So if I plug in 1 to the square root of 1 minus x squared, I get 0. And when I plug in negative 1, I also get 0. So that means I basically have a horizontal secant. So if the secant slope, right, and we want Now I can plug in 1 or -1, so f of 1, I get 0. So that means my secant slope is y equals 0. Now for part B, my tangent line, well, think about this. Here, it's a semicircle, right? So it makes sense that that's my secant line. So my tangent line should end up being that. So again, if we do the derivative, we get 1/2, 1 minus x squared to the -1/2 times -2x, which ends up being x over square root of 1 minus x squared. So if we set this equal to 0, we get x equals 0. So when x equals 0, we get 1. So therefore, the tangent line is the equation y equals 1. Okay, increasing, decreasing function. So this is a topic that you covered last year. Just looking at when it increases, basically we're looking for a positive slope. So if you look at the interval that this is increasing, it looks like it's from -2 to 2. Now, in terms of notation, most textbooks will use brackets. Okay, they do include the endpoints. However, there are some textbooks that will use parentheses. So I will tell you both of these are correct. Okay, usually the AP exam and myself, I will usually use the brackets, including those endpoints. But I'll count the -2 to 2 when parentheses also correct. Okay, decreases. So same idea, just with a negative slope. So this is decreasing on the interval from -2 to 2. So I just talked about slope in terms of increasing and decreasing. Slope, remember, is the derivative. So when the derivative is greater than 0, it's increasing. When the derivative is less than 0, it's decreasing. Now, we actually covered this back in the last section. So when it says analytic methods to find the local extrema, find intervals where the function is increasing and decreasing. So first thing I'd like you to do is figure out the domain. Now this is a polynomial. So my domain is going to be -∞ to infinity. Okay, next step. We want to look at any critical points. So to find the critical points, we're going to find the derivative, which ends up being 2x minus 6. Now there are no places where that's undefined. However, we can see at x equals 3, we do have a critical point. Now I'm going to create a number line. Remember, we're going to leave some space above. This is for the derivative. So I'm going to put -∞ to infinity with my critical point of 3. Now if I choose a point in this interval from -∞ to 3, okay, so if it's from -3 or -∞ to 3, let's test 0. Again, we're plugging into the derivative. We do get negative. If we pick something to the right of 3, say 4, plug it into the derivative, we get a positive. So it goes down, then it goes up, so we can see a minimum at 3. Now, I can see my minimum is going to be f of 3. So we go back and do plug into the original. So x squared, so 3 squared minus 6 times 3 minus 12 is -21. Now I can also see where it's decreasing. It's decreasing from -∞ to 3. And then it begins increasing. So it's going to be from 3 to infinity. So all of this is the information that we needed to answer for that. Okay, let's look at another example. So again, we have a polynomial, so I know my domain is going to be from -∞ to infinity. I need to find the critical point, so we're going to do the derivative. We get 3x squared minus 12x. So if I set this equal to 0, I can factor out an 3x, and I'm left with x minus 4. So I actually have two critical points here, x equals 0 and 4. So we're going to create a number line. negative infinity to infinity, was 0 and 4. So I'm going to pick, let's say, a negative number. I'm going to have a negative times negative, so that's positive. Pick a number between 0 and 4, say 1, so I have positive times negative is negative. And then pick something bigger than 4, I'm going to get positive. So it's going to go up, then go down, then go up. So I have a maximum and then a minimum. So my max is going to be f of 0, which is 5. My minimum is going to be f of 4, which is 6 times, I get negative 27. And so let's take a look. We have it's increasing on 2 intervals here. So it's increasing, from negative infinity to 0. And then it's also increasing from 4 to infinity. And then it's decreasing on the interval from 0 to 4. So all of this answers our question above. Okay, our last example. Now this one, if we take a look at the denominator, our domain this time, basically anything but negative 2 and 2. So I'm just going to keep this in mind for when we create our number line. So let's go through and find the derivative. Now you could do a quotient rule, or you can rewrite this as x squared minus 4 to the negative 1, which is what I'm going to do. So I have negative 1 x squared minus 4 to the negative 2 times 2x. So we get a negative 2x over x squared minus 4 squared. Now if I set that equal to 0, I really get just x equals 0 as a critical point. If I look at where the derivative is undefined, I'd get plus or minus 2, but we already excluded those values from the domain, so there's really just one critical point here. Okay, let's take our number line. Now, when I create my number line this time, I'm going to put at negative 2, I'm going to put an open circle, just keep that in mind. I have it 0, and then I'm going to put 2. I'm also going to put an open circle because those values are not in the domain, but I want to keep that in mind for when I have to write intervals of increase and decrease. Also, I don't want to accidentally plug in negative 2 or 2 into the derivative because then I'll get 0 in the denominator. So I basically have 2 intervals to check. Anything to the left of 0, so I really can plug in negative 1. If you want to plug in something to the left and to the right of negative 2, that's fine, but just so you know, you're going to get the same answer. So if I choose a negative 1, I'll get positive here. I'll also have positive here as well. Pick something to the right of 0, say 1, I'll get negative. Now we get negative here. So it's increasing, continues to increase, decrease, continues to decrease. So I really have just one maximum value. So I have a maximum f of 0. So if I plug in 0, I get negative 1/4. And then where is the function increasing? So when I write this out, it's going to be from negative infinity to negative 2, parentheses, and then union negative 2 to 0, bracket. And then I see it's decreasing on, now we want from 0 to 2, parentheses, and then union 2 to infinity. Again, we want to just make sure that we exclude those values as we're writing the interval.